Hello, this is Hotom Taifa. We carry on with our discussion of state space controller design. In the previous lecture, we focused on the design of a state feedback control matrix, and some of the things we looked at were design specifications, basically how the performance requirements for our designed control system are specified. So this can be stated in terms of the transient and steady state response characteristics, or it can also be in terms of the desired closed loop pole locations. So what's important to remember here is the relationship that exists between the closed loop pole locations and the transient and steady state response characteristics of a control system. We also looked at how to, based on the design specifications, how to go on to design our state feedback control matrix, starting from determining the system's complete controllability, right on to calculating the elements of the state feedback matrix. The other thing that we looked at was how to design for both transient and steady state response. We saw that if we just focus on the transient response characteristics, we might end up with a system that does not perform so well in terms of the steady state accuracy. So one way of dealing with that is to combine state feedback and output feedback control. And specifically, we looked at the incorporating integral control into our state feedback controller, so that we eliminate the steady state error for a step input to a type 0 system. Now, one other thing that we have mentioned in a previous lecture is that state feedback control implementation requires the availability of the entire state vector for feedback. So now what happens if for some reason some of the state variables are not available for measurement? Well, this is where the component known as the state observer comes in, and we are going to look at how this is used in a case where our entire state vector is not available for feedback. So the function of a state observer is basically to enable us to estimate some of the non-measurable state variables of the system. It takes in the control input and measured output, and based on these two inputs we are able to determine the non-measurable state variables. Of course, this requires that the system have the property of full observability, and we have looked at how to check whether a system is fully observable in a previous lecture. So based on this, then if a system is fully observable, then we are able to use the state observer to reconstruct the state vector, which can then be used in the state feedback control topology. So the state observer can be considered to be a subsystem of the entire control system, and because we are trying to estimate the state vector, we find that the mathematical construction of our state observer is in many ways similar to that of the plant or the system to be controlled with a few additional terms. And in terms of the characterization of the state observer, the most important consideration is the minimization of the estimation error. So we will see that the state observer model is characterized mainly in terms of the estimation error. So we have a block diagram here representing a control system, state space control system, and what we see here is that we have a representation of the plant to be controlled on top, and at the bottom we've got an observer. So this system implements a state feedback control, except that for the state vector that we use for state feedback control is derived from the observer. So one thing to note here is that the two systems are quite similar in many ways. What we notice, the main distinction is that the state observer has got an additional term which is constructed from a comparison between the measured output and the estimated output. So this difference between those two signals is then scaled by this matrix L and is then added to the input to our observer. So our system is represented by this model as we know it. It does not have any direct transmission, so it's given by the state equation and the output equation like that, and because of the similarity between our system and the observer, we can construct the observer model based on the state equation. Here the observer model uses x tilde to represent our state vector, so this x tilde corresponds to the observed state vector, and in line with what we have depicted in the block diagram, we've got an additional term that is derived from this comparison between the observed output and the measured one. So we have this additional term to our observer model, and this basically allows to take into account the estimation error. So if we further expand on that, we end up with the expression according to equation 2 as a representative of our observer model. Now, as mentioned earlier, the most important consideration for the state observer is the characterization of the observer model in terms of the estimation error. We achieve that by combining equations 1 and 2 so that we characterize this in terms of the estimation error. According to this expression, we can define a new variable, E, which is basically the difference between the actual state and the observed state. So this stands for the estimation error, and then this allows then our observer model to be recast in the form of an expression that is a function of the estimation error. So this can be considered to be another state variable, rather a state equation, but then the state variable in this case is actually the estimation error. This is a differential equation. The solution of this leads to the error trajectory as given by equation 3. Now it's interesting to note here the parallel between this error trajectory and the state vector trajectory that we are familiar with, which is basically a function of the exponential function, or the state transition matrix A minus B times K. So in this case also, the error trajectory is a function of this exponential matrix given by the expression A minus L times C. So accordingly, from here we can deduce that the error dynamics are defined or determined by the exponential matrix A minus L times C. So the next logical step is now to probably look at when we are designing an observer, what are the objectives that we want to achieve. Well, these objectives revolve around how to shape the error dynamics, because this is an estimation problem. Ideally, we want to minimize the error, the estimation error. So the design objectives can be stated in terms of how the error is supposed to behave. So if we start initially with a zero error, which simply means that the observed state vector is equal to the actual state vector, then we desire this condition to be maintained for all time greater than 0. Okay. Then if the initial error is non-zero, which simply means that the observed state vector does not coincide with the actual state, then as time goes on, we want these two to eventually be equal, which means that the error should be 0. So the error should be driven to 0 as time approaches infinity. And from our discussion of the state vector trajectory, we know that this basically defines an asymptotically stable system. An asymptotically stable system is one where the state approaches 0 as time approaches infinity. So the way we achieve that is basically by designing our system in such a way that the exponential the exponential matrix leads to an asymptotically stable system. So that now translates into finding the suitable value for the gain matrix L, which makes this system asymptotically stable, and that is what we are going to look at. So our observer design then actually amounts to the right choice of the observer gain matrix L. Now we can consider a few guidelines which are supposed to guide us in the choice of the gain values for our observer matrix. So we remember that the system that we are working with is the error trajectory defined by equation 3. The first guideline is that we want to minimize this error. Not only that, but we also want to minimize it as quickly as possible. Now we know from this expression that the larger the value of this exponential matrix, then the faster this value is going to decay to 0. So now that hints that we want to design the value of L to be as large as possible, so that the whatever error may be present initially can be driven to 0 as quickly as possible. But we also need to keep in mind that these error dynamics are defined on the basis of the measurement of the output, and we can expect that the measurement of the output is going to be associated with some measurement errors or measurement noise and some external disturbances. So one effect of having a large observer gain may be to amplify those measurement errors or noise. So in setting the value of L to be large, we also want to keep in mind that we do not want to amplify the noise associated with measurement of the output. The second guideline is that because we want to use the the observed state vector in the state feedback control, we want to have that ready as quickly as possible, which means that the dynamics of the observer subsystem must be much faster, so that we have a sufficiently accurate state vector to implement the feedback topology. One other guideline obviously is to keep in mind that just from the first guideline we can see that there's a bit of a conflict here. We want L to be large so that the error dynamics are as fast as possible, but we also do not want it to be too large in order to suppress measurement errors and disturbances. So we find that it's a bit of a trade-off between having a sufficiently high speed of response and also being able to suppress measurement noise and external disturbances. So we've got an example to look at here. We are given a problem to design a state feedback controller, and this state feedback controller is going to use a state vector derived from a state estimator or an observer. So this is a pole placement problem where we have to place both the closed loop system poles as well as the observer poles. Now we can probably begin by looking at the state feedback gain matrix design. This is what we spent quite some time on in the previous lecture, looking at how to go about designing a state feedback matrix. So because in this lecture our focus is on the state observer design, we are just going to look at how we can obtain the state feedback gain matrix from MATLAB. We can easily do that by implementing the code displayed here as we discussed in the previous lecture. And once we evaluate that code, we find that the state feedback gain matrix is given by it has the elements 29,6 and 3,6. Then we can move on to the observer gain matrix design. We will see that the observer gain matrix design is in many ways similar to the state feedback controller design. In this case, the first step is to determine whether this system is fully observable. In the case of the state feedback gain matrix design, we had to check that the system was completely state controllable. Here we want to ensure that the system is fully observable. For that, we construct or define the observability matrix, which has got the elements C transpose, A transpose times C transpose for this second order system. When we substitute the matrix and the vector there, we end up with observability matrix, which is basically an identity matrix. It's got a determinant, a value of 1, and since this is non-zero, we conclude that the system is fully observable. The next step is to define our desired observer closed loop characteristic equation, similarly to what we did for the state feedback control design. In this case, this is constructed from the given observer poles. We have observer poles given by S sub 3 and S sub 4, and again the closed loop characteristic equation is basically an expansion of the factors in S and whose roots correspond to the desired observer poles. So when we expand that, we end up with a polynomial s squared plus 16s plus 64. The next thing is to determine now the closed loop characteristic equation with the observer implemented. Again, we remember our error dynamics are defined by this equation, and so the characteristic equation is based on this exponential matrix A minus L times C. So it takes the form Si minus A plus L times C. Here Si is a second order, or a 2 by 2 diagonal matrix with S on the diagonal. The L matrix is basically a column vector. It multiplies with C, which is a row vector, and for the matrix multiplication to be valid, we require that L be a column vector. So when we simplify that, we end up with this matrix, and the determinant of that is given by this second order polynomial in S. It's got the variables L sub 1 and L sub 2, which are the elements of our observer matrix. The next step is now to determine the value of L, and based on our desired closed loop characteristic equation and the closed loop characteristic equation implementing the observer, similarly to the approach for the state feedback gain matrix determination, we compare the coefficients of S for these two polynomials. When we do a bit of algebra there, we establish that the elements of this matrix are given by 16 and 84,6. So again, you can see that the observer design is in many ways similar to the state feedback gain matrix design. So because of that similarity, we can basically determine the observer gain matrix using the same functions that we used for the state feedback gain matrix, the functions ACA as well as place. In this case, the input arguments are the state matrix A, the output matrix C, and the vector P, which basically contains the desired observer poles. One thing to note here also is that the state and output matrices are transposed, and we can understand the reason for this when we also think about how the observability matrix is constructed. It also requires the state and the output matrices to be transposed. We also notice that the result of implementing this function is also transposed, and the reason for this is that normally these functions give us a row vector. Remember that the state feedback gain matrix is a row vector. In this case, our observer matrix is a column vector, so we need to transpose it so that it corresponds to what we get from the hand calculations. So perhaps we can go to MATLAB and try to compute this, and just to check with what we got with the hand calculations. So here we have we have defined the state matrix, the output matrix. We have defined the vector P containing the desired observer poles, and then we implement the function ACA, having the input arguments A transpose, C transpose, and P. So we can just evaluate that to see what we get. Okay, so we can see here that we when we evaluate that, we also get the values that we got from our hand calculations, 16 and 84,6. I just noticed here that I had actually not applied transposition to the output of the function echo. But if I do that and evaluate it again, then obviously we get L being a column vector as we desire it to be. So maybe one question that you might ask is why is it that I chose to use the function echo? Is it possible to use the function place in this case also? Well, the answer for that is no. As you will remember from our discussion of these two functions, that they have some limitations. One limitation associated with the function place is that it cannot place a multiple poles. So for interest's sake, we can try to run to evaluate the observer matrix using the function place and see what result we get from that. Okay, so when we try to evaluate the observer matrix using the function place, we see here that it gives us an error, and it says the command cannot place poles with multiplicity greater than the rank of B. So we see here the poles that we want to place have got a multiplicity equal to 2, but when we look at the matrix B, it's got a rank equal to 1, and therefore in this case we are not able to use the function place. So that's just one thing to keep in mind when dealing with functions like this. So basically that is the procedure for determining an observer. For any dimension of a system, when it comes to observer design, the hand calculations become quite involving for systems of order 3 and greater, and that is where computational tools such as MATLAB are very useful. So for the system that we have been looking at, basically this is what it would be implemented like. Now we've got both the state feedback gain matrix and the designed observer matrix. So on top we implement the state feedback control system. At the bottom we implement a state estimation, and the inputs to the observer are the control vector and the output vector, and the output is the observed state vector, which is then used to implement the state feedback control. Now, one of the advantages of state feedback control, as we discussed earlier, is that it allows us to design an optimal control for the system. So in this case, we are going to talk about an optimal state feedback control design. And specifically, we are going to talk about a quadratic optimal regulator, which is basically another approach to the design of a state feedback gain matrix. The other approach which we have been looking at is referred to as the pole placement approach, and the reason is because in designing the state feedback gain matrix, we start with specifying the desired closed loop pole locations on the complex plane. So the way we go about designing the state feedback gain matrix is so as to place the poles at the desired locations. In this case, in taking the approach of the quadratic optimal control, the basis for designing the state feedback controller is to optimize some performance index in addition to achieving the desired transient and steady state response characteristics. So one important consideration in a controller design is the amount of control energy that is going to be expended in implementing our controller. So we have to be mindful of that, because although a certain control system may perform very well in terms of transient and steady state response characteristics, if it requires a lot of control energy, then the efficiency of the overall system might be low, and that might be a problem. So here we are going to look at the optimal state feedback gain matrix design by means of a quadratic optimal control, so as to optimize the control energy as well. So we still begin with our system represented by the state equation according to equation 4, and we want to implement a state feedback control law given by equation 5. In this case, not necessarily to place the poles at the desired locations, but in order to optimize the performance index J given by equation 6. This performance index is in the form of the integral of two quadratic terms. The first term corresponds to the control error, which means it's basically associated with the state vector, the accuracy of the control. The second term is associated with the control vector, and this allows us to take into account the control energy expenditure for this control system. Q and R are positive definite symmetric weighting matrices. So as I mentioned, the two terms of this performance index allow us to take into account both the control error and the control energy expenditure, and basically these weighting matrices Q and R allow us to set the relative importance of these two measures of performance. So in designing the state feedback control matrix, we want to design a matrix K that minimizes the performance index as expressed in equation 6. And if we can find that value of K which minimizes 6, then we have the optimal state feedback gain matrix for any given initial state x of t sub 0. The closed loop system is given by equation 7 with the state feedback gain matrix implemented. Now in finding the solution of the optimization problem, because we want to minimize the performance index with respect to the optimal gain matrix, we want to express the performance index in terms of the state feedback gain matrix. So we do that by substituting the control law 5 into 6, and this leads us to the expression given by equation 8. So in arriving at the solution for the performance index optimization, we assume the solution of 8 to be a quadratic expression x transpose px, and this is the reason why this design approach is referred to as a optimal, a quadratic optimal control. In this case, P is a positive definite symmetric matrix. So if we apply the differential operator to both sides of this expression, then we end up with this expression. Basically, the derivative operator applied to the left hand side gets rid of the integral operator, and on the right hand side we apply the differential operator to this quadratic expression x transpose px. Here we apply the product rule of differentiation, and we get the expression x dot transpose px plus x transpose px dot. X dot is given by equation 7, so we can make that substitution, and we end up with this expression. So then we can compare the left hand side and the right hand side, and we end up with this expression where we basically have both on the left hand side and on the right hand side we've got quadratic expressions, and this means that the terms in the parentheses are equal. So we can forget about the state vector for now and just make a comparison between the terms in the parentheses, and we end up with the expression given by equation 9. So this is basically the equation that characterizes our optimization problem, and it is derived from equation 8 for the performance index by substituting the control law u equal to minus kx, and making the assumption that the result of this integral is a quadratic expression x transpose px. So if we can find the solution for this expression 9, then we have the solution of the optimization problem. Before we find the solution for equation 9, it is convenient to look at how we are going to evaluate the performance index J from 8. Now the solution of 8 is, or the result of this integral is assumed to have to take the form minus x transpose px, and this is the result of integrating this. So we are going to find we are going to evaluate this solution between the limits of integration infinity and 0, and what we get from that is this expression having two terms. The first term depends on the steady state value of the state vector and the positive definite matrix P. The second term depends on the initial value of the state vector and the positive definite symmetric matrix P. Now if we remember what the expression for the state vector is, we realize that this expression it allows us to have an idea of what we are going to have in the steady state. Here we assume that the exponential matrix A minus B times K has got eigenvalues with negative real components. What that means is that in the steady state the the state vector is going to go to 0 as time approaches infinity. Okay. The significance of that is that it allows us to conclude then that the performance index is a function of only the initial state vector and the matrix P. Okay, so knowing our initial condition and knowing what the value of the positive definite matrix P is, we are able to evaluate the performance index. So provided that the matrix A minus BK is stable, we are able to find a positive definite matrix P that satisfies equation 9, and that is the matrix that enables us to determine the optimal state feedback gain matrix, as well as to evaluate the performance index J. So the solution of the optimization problem boils down to finding the positive definite matrix P that satisfies equation 9. So we can see here equation 9 is a function of both matrices P and K, in addition to the other matrices A and B and R. So in finding the solution to the optimization problem, firstly we are going to minimize equation 9 with respect to K. This approach is taken so that we can find the solution, the value of P. In this case, we are not able to do that because equation 9 is still a function of both P and K, and both are not known at this stage. So we can just rewrite this expression 9, getting rid of the parentheses. So we apply the transposition to the terms in the parentheses. We get, and then we multiply by P. So we get A transpose P minus B K transpose P. Then we can multiply throughout here. We get PA minus PBK, and then we add the rest of the terms. Then we can get rid of this parenthesis also by applying the transposition to the terms in the parentheses. Here we want to remember that the transpose of a product of two matrices is equal to the product of the transposes of the matrices, but in reverse order. So then we can take the derivative of the partial derivative of 11 with respect to K, and here the first three terms do not have any K, so they fall out. The derivative of this term with respect to K will be B transpose P, and it's supposed to be transposed because K is in form of a transpose. The next term, the derivative of this with respect to K, gives us PB, and here we have to apply a product rule of differentiation because we've got two K's here, so we get these two terms. Simplifying that, we get from the first term PB by applying this rule for transposition, and remembering that the P is a symmetrical matrix, so P transpose is equal to P. Simplifying that further, we get these two terms add up to minus 2 PB, and we can combine these two terms again here, remembering that R is a symmetrical matrix, so R transpose is equal to R. Simplifying that further, by we can take this term to the right hand side, and divide throughout by 2, we get transpose K transpose R is equal to PB, and making K the subject of the formula, we get the expression for K given by equation 4, which is R inverse B transpose P. So this is basically the solution of the optimal state feedback gain matrix. It is expressed in terms of the weighting matrix R for the control energy expenditure, the control matrix B, and the positive definite matrix P. So as long as we know the values of this, then we can determine our state feedback gain matrix. To find the solution of the optimization problem, we are going to now substitute the expression 12 into 9 so that we can find the solution of P. And this once we make that substitution and do a bit of algebra, we end up with the expression given by equation 13. This is referred to as the reduced matrix Riccati equation. So this matrix is no longer a function of the state feedback gain matrix K rather. The unknown here is the matrix P. So the procedure then for finding the solution of the optimization problem is to determine the positive definite matrix P, which satisfies equation 13. Okay. In order for us to be able to do that, because it's just one equation, we require that only P be the unknown element. So we obtain A and B from the system to be controlled, and the weighting matrices Q and R then have to be specified so that we can determine the value of P. So once we have determined the value of P, that satisfies equation 13, which has to be positive, definite, and symmetric, then we can use that in equation 12 to find the value of K, which is our desired optimal state feedback gain matrix. We are going to look at an example. So we are given a second order space system. The weighting matrices Q and R are specified, and we have to determine the optimal regulator for this system. In addition to that, we have to determine the closed loop stability of the system based on the Lyapunov stability theory, and the matrix P for that is specified. So because this is a state feedback control design problem, we begin by determining whether this system is completely state controllable. For that, we define our controllability matrix, which in this case is given by this matrix 0, 1, 1, 1, which has a determinant equal to -1, and since this is not equal to 0, we conclude that this system is completely state controllable. Now the next step in the quadratic optimal regulator design problem is now to determine the positive definite matrix P, which satisfies the reduced matrix Riccati equation. Restated here, it's A transpose P plus PA minus PB R inverse B transpose P plus Q equal to 0. So in this reduced matrix Riccati equation, the only unknown is P, which is what we have to solve for. Okay, we've got A, we've got B, we've got R, and we've got Q. So we can substitute all of those into our reduced matrix Riccati equation. P here is expressed in terms of the unknown elements P11, P12, and P22. We just want to be careful here to make sure that we transpose A as the first element. We take the inverse of the weighting matrix R. In this case it's just 1, so R inverse is equal to R in this case, and then we transpose B as well. So an intermediate step in solving for this, the first term here evaluates to this, the second term evaluates to this, then here we multiply this matrix with this to get that, and we multiply this with this to get that one, and then we just bring down the matrix Q and the zero matrix. Simplifying it further, we end up with this expression here. So having this expression, then we have to solve for the elements of the P matrix P11, P12, and P22. Firstly, we can take the first term because that one has got only one unknown P12. From that we find that P12 has got two values, -1 and +1. So for each of those values we have to find the corresponding values of the other elements P11 and P22. So taking the positive value of P12 and noticing that the fourth element of this matrix has got two unknowns P12 and P22, we can solve for P22 because now we've got the value for P12. So evaluating that, equating it to 0, gives us this quadratic expression which is factorizable and allows us to then determine the values of P22 to be -2 and 4. So for the one positive value of P12, we get two values of P22. From that we can determine the value of P11 using this element here, and we find that it also has two corresponding values, -3 and +3. So we just want to ensure here that we associate the right elements. So a +1 for P12 is associated with a -2 and -3. It is also associated with a +4 and +3. Okay. Taking the negative value of P12 and following the same procedure, we end up with a quadratic expression in P22, and because this is not factorizable, we can apply the quadratic formula and find that the values for P22 corresponding to the negative value of P12 are 3,236 and -1,236. Then again, using this element, we can find the value of P11 to be respectively -2,236 and +2,236. This is tabulated for us here to present it in a more convenient form. So we've got four sets of values for the matrix P. And the next thing here is to determine the positive definite matrix P, which satisfies equation 9. Okay, so the claim here is that we only have one positive definite matrix that satisfies equation 9, provided that the matrix A minus B times K is stable. Okay, so we are going to go through the procedure of of determining the positive definiteness of the matrix P based on all these elements of the P matrix. Okay. Starting with the first one, given by -3, 1, 1, and -2, we find that this matrix is not a positive definite. Just to mention here how to determine whether a given matrix is positive definite or not, we look at the leading principal minors. Okay, so the leading principal minors are given by looking at the diagonal and starting with the first term. So this is the first leading principal minor obtained by getting rid of this column and this row. The next leading principal minor would be the entire matrix. If it was a 3 by 3 matrix, then the next one would be this submatrix, and then it would be the next one, and so on. So we are going to be looking at the determinant of the first element and the determinant of the entire matrix. In this case, the determinant of the first element is negative, so we conclude that this the matrix P using the first set of elements is not positive definite. Next, we look at the next set of elements. Here, the first a leading principal minor has got a determinant which is positive, and the entire matrix also has a determinant which is positive, and so we conclude that this the matrix P using the second set of elements is positive definite. Now for this optimization problem, we expect to get only one positive definite matrix. Otherwise, we would not be able to determine the optimal state feedback gain matrix if we were to get two matrices P that satisfy equation 9. Now, it is necessary nonetheless to show that all the other matrices are not positive definite. So we will go ahead and look at the positive definiteness of the matrix built from the other elements. The next one, okay, it is easy because we see immediately that the first term is negative, so this is not positive definite. The next one, the first term is a positive. It has got a determinant that is positive, but when we look at the determinant of the entire matrix, we find that it is negative. Okay, so we have proved that there is only one matrix which is positive definite, and it is built from the second set of elements. Okay, so having obtained the positive definite matrix, now we can obtain the state feedback matrix K according to equation 12, and this gives us the matrix with elements 1 and 4. So this is the optimal gain matrix K that we had to determine. We are able to determine the optimal gain matrix also in MATLAB. It provides a function LQR, a linear quadratic regulator. For this, we have to define the state matrix A, the control vector, and the weighting matrices Q and R, And the syntax for implementing this function is it takes the input arguments in this order: A, B, Q, and R, and the outputs are the optimal gain matrix K, the matrix, the positive definite symmetrical matrix P, and the closed loop eigenvalues of this system, which we get once we have implemented the state feedback gain the matrix. So if we were to evaluate this in MATLAB, we would get the value for K 1 and 4, P 3, 1, 1, 4, and the closed loop eigenvalues negative 2,618 and negative 0,382. So it is a good idea to, if you are able to just do this also in MATLAB, to double check and confirm that what you got from the hand calculations are correct. Okay, so as I mentioned, from here, K is the optimal gain matrix, P is the solution of the Riccati equation, and E the closed loop eigenvalues. Okay. So there is a function in MATLAB, EIG, that allows us to determine the eigenvalues of a matrix. In this case, if we are interested in finding the closed loop eigenvalues, then we are still able to do this by means of this function. Okay. So perhaps we could go to MATLAB and evaluate this code and just to see what we get. Okay, so we can see that we actually get the same values as was shown in the slides. I have suppressed the other outputs just because the interest here was in showing how we can get the eigenvalues of a given matrix. We could use the same function to get the open loop eigenvalues simply by looking at so we can see here that we get these are the open loop eigenvalues, and then we are able to compare the open loop eigenvalues with the closed loop eigenvalues, and perhaps we are able to also determine what difference implementing the state feedback gain matrix, the difference that it makes in both the eigenvalues as well as the closed loop response of the system. So the next thing that we want to do now is to determine the stability of the closed loop system, and for that, firstly, we want to work out the closed loop state matrix, which is given by the expression A minus B times K. Okay, so we are going to use the Lyapunov equation, A transpose P plus PA equal to minus Q. Here we have been supplied with the positive definite matrix P that we can use to test the stability of this system, and the idea is to determine the matrix Q and see if it is a positive definite. If it is positive definite and symmetrical, then we conclude that the system is asymptotically stable. If it is if the matrix Q is not positive definite, then it simply means that the system is not, the closed loop system is not stable. Okay. So substituting the values of A transpose, remember that we have to use the closed loop one because we are looking at the stability of the closed loop system, and using the P that has been provided, we obtain that. Here we can factor out the negative and look at the positive definiteness of that matrix. Okay. So firstly, the determinant of the first term there is greater than 0, and the determinant of the whole matrix Q is also greater than 0. From this we conclude that since Q is positive definite, the system is the closed loop system is stable. So and this is the basic procedure for going about designing a quadratic optimal regulator. What we want to remember is most important is that obviously once we have determined that the system is completely state controllable, the next step is to find the positive definite matrix which satisfies the reduced matrix Riccati equation. And we are going to get a set of values for P, and we have to evaluate the positive definiteness of all of them. Normally we find only one P that is positive definite and satisfies the reduced matrix Riccati equation. Then we use that to calculate the optimal state feedback gain matrix. Then if the question specifies it, then we also need to check that the closed loop system is stable. If we find that it is not stable, it may be necessary to modify the weighting matrices Q and R, because these are basically the ones on the basis of which our quadratic optimal regulator is designed. So if maybe the requirements here are too maybe they cannot be satisfied by a quadratic optimal regulator, then we may need to modify these design requirements. In this lecture, we have also looked at the design of an observer, which may become necessary if not all state variables are measurable, and we desire to implement a state feedback controller. So this brings us to the end of our discussion of state feedback controller design and all the aspects associated with it. The next topic that we are going to look at sampled data systems and digital control systems. Thank you very much for watching.